This next video is about the magnetic field, which we're going to talk about more in class. I want to give you enough of an understanding that you can make some measurements of it in a lab this week or the week after break, particularly with a device which is a coil of wire. Coils of wire, as you'll find out, are really important. This coil of wire is called a solenoid, and a good example of a solenoid is what you're going to use in lab, a slinky. It's a solenoid, so you're going to be using that in lab to create a magnetic field. And the idea behind a magnetic field, by the way, what is a magnetic field? A magnetic field, you can think of it's different from an electric field. It's a type of field. They're related, as we'll see later. But a magnetic field is the direction that a compass is going to point. So a compass will point in the direction of a magnetic field. So I'll just make that point here. Alright, so it's not the direction that a charge would experience a force, so it's different from electric field, and I'm going to put that in capital letters because that often gets confused. It does not affect a stationary charge. We'll talk about what it affects later. But a magnetic field will attract pieces of metal. If you've ever played with magnets, you'll have the experience of doing that. You can actually create magnets using wires, as we're going to do in class today. If you wrap them around a piece of iron, you can get a really strong magnetic field. And we'll talk more about that later. The point is, in lab, you are going to measure the magnetic field associated with putting a current, I, through a coil of wire. So what the current does is it follows the coil. So if it follows the coils, each of these coils has current running through it. And we'll talk about in class the fact that as a result of this, I'll draw what the magnetic field will look like. We'll talk about the direction in class. It's hard to show on this drawing here, when you're drawing a coil, what is the direction of the coil? Is it clockwise or counterclockwise? But the current that flows through the coil will create a magnetic field depending on whether the coil is wound clockwise or counterclockwise. The magnetic field will either be to the left or to the right. And the symbol for the magnetic field is capital B, and it's going to be uniform within the coil. So it's going to have the same value anywhere in the coil. Something you'll need to know, because most of the time the magnetic field is not uniform. It's going to vary, both in direction and in size, just like the electric field will tend to, except for just one case, which we'll also talk about soon. So uniform means the same everywhere. So when you're measuring it in lab, it doesn't matter where you put the probe inside the coil, which is what you're going to be doing in lab, is measuring how strong the magnetic field is in the coil. So one of the things you'll see in class eventually is that the magnetic field, B, the size of it, is equal to, and so it's the size of a vector quantity, which is equal to just B, is equal to the current times the number of coils per unit length times some constant, a new constant, which is something I'm going to give you called mu0. This is a new constant. What you're going to be doing in lab is measuring the size of this constant, mu0. It's new for us. Alright, so what is this n? This n refers to the number of coils per unit length. Not a hard concept, but one that does get confused by students the first time they see it, and of course I is the current. I'm going to talk about this little n in a minute. Okay? So this is the equation that you will need to know and use in lab, knowing that what you're actually going to be calculating is mu 0. You're going to be measuring the magnetic field. So this is what you're going to calculate. This is something you can measure. We have probes that can actually be used to measure the magnetic field. You'll know the current because you can control that with the power supplies that you'll be using. There's a certain setting that you'll push it in that you'll see in lab that will allow you to adjust the current, and that's what you'll be changing. You're going to try to get it up all the way to 1 amp if possible, if you have power supplies that'll do that. And I'm going to talk about N on the next slide, but that's something you can also measure. So, I'm going to draw you here two different coils, one that has a high N and one that has a low N. So the high N coil will look like this. It's a big value of number of coils per unit meter, per unit length. And this is a small N. It's a big N, small n. And the idea here is, or the way to calculate it is, you actually count the number of coils and you look at the length over which you're counting the number. So you might pick a length, let's say it's 10 centimeters, just for instance. And let's say we count 5 coils in here. I see 1, 2, 3, 4, 5. So my little n is then going to be 5 coils per 10 centimeters, which would be equal to 50 coils per meter. So this little n then reflects the number of coils per unit length, and since we're using metric, we're going to use the meter as our unit when we're actually using this in an equation. You want to convert it to coils per meter. Alright, so that will set up. In lab, what you're going to be doing is generating or spreading out your slinky, either tightly or loosely. I think you use 3 different configurations. You get to pick the number of coils per unit meter based upon how much you spread out your slinky. And then you will, for each spread that you use for the slinky, you will adjust the size of the current that you're passing through the slinky. You'll start at 0 amps, and you will ramp up. You go 0.1 amps, 0.2 amps. And if you have a power supply that can handle it, you'll go all the way up to 1 amp. Some of the power supplies only are able to get to about 1/2 of an amp. So I'll have you go as high as you can. If you can only go to 1/2 of an amp, you only get 5 or 6 data points for that. If you can get up to 1 whole amp, then you'll have 10 data points. And what you're going to do is you're going to the magnetic field that you're measuring through the coil using a vernier magnetic field probe versus the current for different values of N. So you'll have you'll have 3 plots because you're going to be using 3 different spacings of the slinky. So for each case, you'll plot the magnetic field versus the current. And from that plot, you might be able to guess what the plot's going to look like. I'll have you think about that. What sort of a function should the plot look like for a coil? As you increase the current, what's going to happen to the magnetic field? What is that relationship? Is it going to be linear, or is it going to be something else? What do you think? I think you'll see when you actually graph it. And then from this graph, I want you to try to determine what is the value of this constant, mu 0. And I'm going to give you its value right now. It's equal to 4 pi times 10 to the minus 7th. And the units of this would be Teslas, which I neglected to tell you a minute ago. Teslas ampere meter. That's the unit of mu 0. Now the Tesla, by the way, is the unit of the magnetic field. I neglected to say that earlier. So the magnetic field B has units of Teslas. Current has units of amperes, as you already know. And this little n is it's the number of coils per unit meter. So the units of n are 1 over meters. So it's actually the number. So n is really the number of coils, and implicitly per unit meter. But you don't have coils in the units of n. So if you multiply B times n times I, you will get units of Tesla for B. And your magnetic field probe measures in units of either Tesla or millitesla. So that will give you the conversion you need to compare all of these and to see if you can calculate the value of mu 0 from your data, which should be close to this number. You'll find the percentage difference between them. And that's essentially what you'll be doing in lab. Okay, see you in lab or in class.